of bond energies, define exothermic and endothermic reactions in terms of bond energies and enthalpy changes. You should be able to define enthalpy, interpret an enthalpy profile, use enthalpy values to classify reactions, and you should be able to explain activation energy. Our key focus areas: bond energy, endothermic reactions, exothermic reactions, enthalpy, and activation energy. We begin by investigating energy changes in chemical reactions. Now we have what we call exothermic reactions, and an exothermic reaction gives out energy, sometimes in the form of heat, sometimes in the form of light or other energies. An endothermic reaction, on the other hand, takes in energy from the surroundings. Now recall, bond energy is the amount of energy required to break or the amount of energy required to form a bond. Now there are two stages that are involved in a chemical reaction. Stage 1 is where you have bonds breaking, and basically it is the bonds of the reactants that break, as shown in that diagram. And this stage is generally endothermic. The next stage is the formation of new bonds. In other words, when we form new products, where you form bonds as shown over there. And that process, or that stage, is generally exothermic. Now, the stage with the largest energy change therefore determines if the overall reaction is endothermic or exothermic. To explain this further, let's use this example. For example, methane reacting with oxygen to form carbon dioxide and water. And here are the reactants and the products in formula form. Now stage 1, the endothermic stage, where we have bonds breaking. If we first look at the CH4 molecule, the CH4 molecule has 4 CH bonds. It's got 4 carbon-hydrogen bonds. And the amount of energy required or taken in to break these bonds would therefore be 414 kilojoules per mole for one CH bond, and we've got 4, so we multiply that by 4. But also, the oxygen molecule has got double bonds between the oxygen atoms, and the amount of energy required to break these bonds is 499 kilojoules per mole for one bond, and so we multiply that by 2. And so the total energy that is needed to break the bonds in the reactants is basically the sum of all these energies, and we then need 2654 kilojoules per mole. Stage 2, the exothermic stage, energy released stage. Well, if we look at the amount of energy released when new bonds are forming, where we look at the carbon dioxide molecule, where we form 2 CO bonds, and so the amount of energy released is 799 kilojoules per mole times 2. And if we look at the water molecule, here we have 4 oxygen-hydrogen bonds, and the amount of energy released is 4 times 460 kilojoules per mole. And so if we look at the total amount of energy that is being released, we have 3,438 kilojoules per mole that is released. And therefore, the amount of energy that is released or given out is greater than the amount of energy that is taken in, and therefore the overall reaction is exothermic since it releases energy. What is the concept of enthalpy? The change in energy that results when reactants form products is called the heat of the reaction. At constant atmospheric pressure, the heat is called the enthalpy change of the system. And so enthalpy is the total amount of energy of the reactants or the products. And the symbol that we use for enthalpy is capital H. An enthalpy change, enthalpy cannot be measured. So H cannot be measured, but we can measure change in enthalpy, which is delta H. And the units that we use for enthalpy is kilojoules per mole. Next, we look at enthalpy and enthalpy profiles. Now we said that enthalpy is heat of the reaction, and heat of the reaction is basically the heat of the products minus the heat of the reactants, or enthalpy of the reaction equals to enthalpy of the products minus enthalpy of the reactants. And so the formula is delta H equals to H of products minus H of the reactants. If you look at an exothermic reaction and we plot a graph looking at the enthalpy change, we'll notice that in an exothermic reaction that the heat is given out, which means that the enthalpy of the products is less than that of the reactants. And this space over here, this gap over here, will give us an indication of the enthalpy change, delta H. And as we have said, in an exothermic reaction, the enthalpy of the reactants is greater than that of the products. And so the delta H, basically the difference between that, the enthalpy of the products and the reactants, is negative in an exothermic reaction. If we look at an endothermic reaction, again there's our graph. You'll notice that the reactants this time have got less heat than the products. So in this case, heat is taken into the system, and there we can calculate our delta H. And because the enthalpy of the reactants in this case is less than that of the products, delta H is positive. So in an endothermic reaction, delta H is always positive, and in an exothermic reaction, delta H is always negative. Another concept that we must talk about is the concept of activation energy. Most reactions do not begin spontaneously, as you might know this. There is a minimum amount of energy that is needed for a reaction to actually begin, and that amount of energy is called the activation energy. So the activation energy is often called the energy hill, which the reaction must overcome before it can proceed. When the activation energy is then added to the reactants, a so-called activated complex is formed. An activated complex is basically a temporary unstable composition of the reactant atoms, or a transition state between reactants and products. In other words, if you react compound A, B, and C, you have this state before you actually form the products. In this case, perhaps compound A and BC, you have this complex here called the activated complex. What actually happens there is basically where new bonds are formed to get the products, or perhaps the old bonds remain to actually keep the reactants. And so that, in our case, would be our activated complex. Energy changes in a chemical reaction can actually be represented by means of a graph. Now let's consider our reaction AB plus C reacting to form A plus BC. And let's say this reaction is an exothermic reaction. And so let's plot a graph of enthalpy versus the progress of this reaction. And basically for this reaction, for an exothermic reaction indicated above, we get a shape like that one if it's exothermic, and that would be the enthalpy of the reactants. And the reaction will proceed as follows, and we get to this point here, and that is where our activated complex would be. And at the bottom here, we then get the enthalpy of the products. Now, because this is an exothermic reaction, you'll notice that the enthalpy of the products is less than that of the reactants. And the gap between this place, the energy of the reactants, or the enthalpy of the reactants, and the activated complex is basically your activation energy. So this is how much activation energy is required for the reaction to proceed. And then, of course, the difference between the enthalpy of the products and that of the reactants is from there to here, and that is delta H. So for an exothermic reaction, a graph of enthalpy versus the progress, if you look at the progress of that reaction, you will get a shape like this one. Now, a challenge for you would be to produce a graph of enthalpy looking at the progress of the reaction, but for an endothermic reaction. One of the things that can have an effect on the progress of a reaction is a catalyst. So we're going to have a look at the enthalpy graph and look at what happens when we introduce a catalyst. Basically, there's our graph. Similar graph is in the previous slide of an exothermic reaction. Now let's have a look at what happens if you introduce a catalyst into this reaction. That is basically what happens. That would be then the shape of the graph. You'll notice that the shape of the graph remains the same. The only thing that changes is the activation energy. In other words, the amount of activation energy required for this reaction, if there's a catalyst involved, becomes less. So we say the introduction of a catalyst basically lowers the energy here. Now there are two types of catalysts. We have what we call a homogeneous catalyst, and we have what we call a heterogeneous catalyst. A homogeneous catalyst is basically where the catalyst is in the same phase as the reactant. So if it's a solid and the reactants are in the solid phase, then we have a homogeneous catalyst. A heterogeneous one, where a catalyst is in the different phase as the reactants. This is quite common, where you introduce a solid catalyst, for example, in a reaction where everything else is in the liquid phase. That would be a heterogeneous catalyst. So a catalyst, basically, it does not cause the reaction to begin. What it only does, it can only increase the rate of the reaction, and therefore it can also lower the activation energy. A quick challenge for you. Consider these three reactions. Classify each of the following as either endothermic or exothermic. Now, I would advise you to stop the DVD at this point, quickly go through these three questions, and then view the solutions later. Here are the solutions. The first reaction is exothermic, the second one endothermic, the third one is exothermic. How I get to the answer is simply I look at delta H. Delta H negative is an exothermic reaction, and delta H positive is an endothermic reaction. Challenge 2. The graph in the diagram below, there's the graph, represents the change in energy that occurs during the reaction of nitrogen with hydrogen to form ammonia. Question 2.1. Provide labels for the X and the Y axis. 2.2. Compare the energy of the products to that of the reactants. 2.3. Is delta H for this reaction positive or negative? 2.4. Is this reaction endothermic or exothermic? Again, please pause the DVD at this stage. Quickly do this challenge on your own and then check the answers later. Well, let's have a look at the solution to check if you are correct. Again, there we must have our graph before we go. First question was to label the axis. Well, on the x-axis you plot the progress of the reaction, on the y-axis the enthalpy. Second question was to tell about the energy of the products versus that of the reactants. If you look at the shape of this graph, you can clearly see that the energy of the products is less than that of the reactants. The third question was to look at delta H. Is it positive or negative? Well, it is negative because delta H is energy of the products minus that of the reactants, and so the products have got less energy than the reactants. Is this reaction endothermic or exothermic? Well, it's exothermic because delta H is negative. I hope this matches your answers. We've come to the end of this lesson. For additional challenges, once again, you go to the Study and Master, the grade 11 copy, and you'll find on page 255 to page 257 activity 4 and activity 5, which will basically give you additional challenges on energy and chemical change. Now please note that for maximum benefit from these DVDs, you must watch each lesson at least more than once and do the worksheets that accompany each lesson.